Hello, calculus students. We're doing notes number 14 today, and the title is Slopes of Secant Lines and Tangent Lines. And this concept today is probably the most important of the entire class. This is really the foundation of what we do in this class, this whole course. So I'm going to explain it to you kind of pictorially first, and then we're going to get into some numerical calculations. So here's the big idea. In this class, we want to know how fast is something changing? What is the rate of change of y with respect to x? Think of some real-world examples. Sometimes we want to know a quantity, like how many vaccines were given, but sometimes we want to know a rate, like how fast are the vaccines being given. And so far, your study of rate has just been the slope of a line, and a line has a constant slope, a constant rate of change. But if you imagine something that's not a line, it's a curve, it would not always have the same rate of change. It would not always have the same slope. So in calculus, we discover how to calculate the rate of change of something that's not linear. So what I'm going to do is draw just sort of some random function. Let's say this is f of x. And let's say that I want to know the rate of change of this curve at a particular point. So you could say I want to know the slope of the curve, but what's the slope of a curve? Okay, that concept we don't really have a well-defined meaning for. So instead, let's say I have this point right here, and I want to know how fast is the curve changing at that point. What we can do is we can draw a tangent line there. A tangent line touches the curve at a single point, and it goes in the direction of the curve. So you see, I could draw infinitely many lines that touch the curve at the point, but these lines are not going in the direction of the curve, so those are not tangent lines. The one that's going in the direction of the curve and touching the curve at one point is the tangent line. We use the word tangent, but it doesn't mean the same thing that it meant when we were doing sine, cosine, and tangent. And maybe when you were in geometry, you studied circles, and you talked about a line that was tangent to a circle was a line that touched the circle in one point. And then you might have also talked about a line that touched the circle in 2 points was called a secant line. Again, we're using the word secant, but it doesn't mean the same thing as it meant with like cosecant, secant, and cotangent. It's a different use of the word. Okay, so back to the tangent line to f of x. I want to know the slope of that line, but I can't get the slope of a line if I only know one point. I need 2 points. So what we do to approximate the slope of the tangent line is we find a second point on the curve. So maybe my first point is point P, and I find a second point, point Q, and I draw the secant line between points P and Q, meaning the line that goes through both of those points. That's the secant line, and because I have 2 points, I can find the slope, and I could use that slope to approximate the slope of the tangent line. But is it a good approximation? Well, maybe. I suspect that if point Q was way out here, that this line between P and Q, imagine that that went through those points, that line would not do a good job of approximating the tangent line. So the slope of that line would not be a good approximation for the slope of the tangent line. However, if the point Q is close to point P, the secant line slope is probably a good approximation for the tangent line slope. So what we do in calculus is we move point Q closer and closer to point P, and we move it infinitely close. So that's where limits are going to come into place. Now point Q could instead be on the other side of P, and then we could move it closer and closer, and we could get better and better approximations for the slope of the tangent line by getting secant line slopes where the 2 points are really, really close together. That's the whole concept of what we're learning this week. Today, what we do is we literally just take 2 points and find the slope. 2 points that are closer and find the slope. 2 points that are even closer, and find the slope. And we do that several times, and that slope is probably going to be getting close to a particular number and will approximate the tangent line slope with that number. So that's the plan for today. And then next time we're going to learn the calculus method for using limits to actually get the real answer for the slope of the tangent line. Okay, sometimes you're going to see me talk about or hear me talk about average rate of change or instantaneous rate of change. You want to think of average rate of change as the slope of the secant line. You have 2 points. You find the slope between the 2 points. That's the average rate of change between those points. But if we're talking about instantaneous rate of change, that's just the rate of change at one instant. That's the slope of the tangent line. It's important to remember the differences between these two. In particular, some of the problems we do have to do with velocity. Instantaneous rate of change would be velocity at a particular point. Average rate of change would be the velocity found by just taking 2 points and finding the slope between them. We're going to work through 3 examples, and they're all very similar, but they have slight variations in how they're presented, which can sometimes trip students up. So I want to show you one of each. So here's problem number 1. We have the point P, which has coordinates 2, 8, and it lies on the curve y equals 2x squared. So what we see here is a graphing calculator version of that curve, y equals 2x squared. And down below it, I've kind of zoomed in on the point 2, 8. So this is point P here. Q is some other point on the curve, and we want to find the slope of the secant line from P to Q. And we're going to approximate it to the nearest hundredth, which is 2 decimal places. And here we have 8 different values of Q. So we're going to start with part A. Q is the point 1.5 comma whatever we get when we take 2 times 1.5 and square it. So that's the y coordinate when the x coordinate is 1.5. Okay, so if we want to visualize this, point Q is right about here. And what we're going to do is calculate the slope of that secant line. Now, we know how to calculate slope. We can calculate each of these slopes one by one, and it's going to get really boring and tedious. So what I'm going to do is show you how you can use your calculator to make a formula for this, and you can calculate them all quickly with your calculator. So we know to find slope, we take y2 minus y1 over x2 minus x1. Well, let's say that point P is our x1, y1, and point Q is our x2, y2. So y2 is 2 times 1.5 squared, but in general, it's just going to be 2x squared. Okay, we're going to do it with 8 different values of x. Minus y1. y1 is always going to be 8 because every time we change Q, we leave P the same. P is always going to be 2, 8 for this entire problem. We're just going to make Q closer to it and closer to it, and on the other side, closer to it and closer to it, etc. On the bottom, x2 is just x, minus x1 is 2. So for this problem, this is like your formula for slope. And every time you want to find a slope with a different value of x, you just plug it into that formula. So in the calculator, we're going to put this into y1. And be careful, you need to make sure that your entire numerator has parentheses around it and your entire denominator has parentheses around it. So let's do that. Here's my calculator. I go into y equals. My numerator was 2x squared minus 8, parentheses around that, divided by, and then parentheses, x minus 2. Maybe your calculator uses special notation and puts it into a fraction mode, and you don't have to have parentheses, but just in case, you might want to put them anyway, and my calculator needs them. Okay, now what I want to do is let the calculator do the work for me, so I'm going to make a table. First I go to Secant, Window, and that's Table Set, and make sure it says Independent Ask. That way the calculator asks you for the x values and you type them in. So once it's set like that, you go Second Graph, and that takes you into Table. Here's where we're going to type in those different values of q. Maybe I should say those different x coordinates as we change point q. So we had x is 1.5. Now the y value, that's not the y coordinate of the point, that is the slope when you use 1.5 for your x coordinate. Remember, the formula that we put into the y equals menu is the slope. Next is 1.9, and then 1.99. So notice that these values for q, for our point q, are getting really close to 2, coming at 2 from the left. What do you notice is happening to the slopes? What are they getting close to? Now from the other side, point Q is coming closer and closer to point P, but coming at it from the right. So we're putting in those different values of Q, and what do you notice about the slopes? Do you notice that as you move toward x equals 2 from the left, and as you move toward x equals 2 from the right, those slopes are getting closer and closer to 8. Okay, so let's go back here, and what you would do is just write down those values for your answers, those slopes. And the next question is, using the results of that problem, guess the value of the slope of the tangent line to that curve at that point. Well, we saw that those slopes were getting closer and closer to 8. Now, using the slope from problem number 2, find an equation of the tangent line to the curve at the point 2, 8. The equation of the tangent line. So let's look for something in the form y equals mx plus b. Now we know the slope is 8. By the way, when you picture this and you think about the point 2, 8, don't you see that that tangent line there is really steep, and that it has a positive slope? And that was a really bad sketch. I didn't really make my tangent line look like it was touching there at 2, 8. But you can see there is a positive slope and it's a steep line. So having a positive slope of 8 kind of makes sense. Take your point, take your slope. If you want, you could use point slope form. Substitute 8 in for y1, substitute 8 in for m, substitute 2 in for x1, simplify. Y equals 8x minus 8. There's a lot of 8's in this problem. Okay, so could you picture that if this line continued down, you would hit the y-axis at -8? That kind of makes sense. All right. So that's the end of that kind of problem. Now we have a similar problem with a similar process, but the wording is different. It's more of an application. If a ball is thrown into the air with a velocity of 25 feet per second, its height in feet after t seconds is given by y equals 25t minus 16t squared. Find the average velocity for the time period beginning when t equals 3 and lasting half a second, a tenth of a second, etc. Now here's what we need to know. Velocity is the rate of change of position. Think about when you're driving and you look at your speedometer. Doesn't it tell you how fast your position is changing? So the velocity is the rate of change of the height. Position could be height. In this case, it's height. It's not always. Sometimes it's more of a horizontal thing. Sometimes it's more of a vertical thing. So we're given our function. And if we're asked to find the average velocity, that means the average rate of change of the position, that means find the slope of the secant line. For the time period beginning when t equals 3. Okay, so that means our point P is 3 something. If you substitute 3 into this function, 25 times 3 minus 16 times 3 squared, you end up with negative 69. So the position at time 3 seconds is negative 69. Maybe we're underground. I don't know, maybe the position 0 is actually at the top of a building. I don't know what the point of reference is for this problem, but for whatever reason, we have a negative position here. Now for part A, the time period lasts 0.5 seconds. So this is giving us our point Q. But our point Q doesn't have an x-coordinate of 0.5. It has an x-coordinate of 3.5. See, we're adding half a second to 3. This is telling us how long the time period lasts. So it goes from time 3 to time 3.5. And then the y-coordinate is going to be 25 times 3.5 minus 16 times 3.5 squared. But just like in the last problem, I'm not going to calculate that. I'm going to make a formula for myself. So the slope is going to be the y-coordinate from point Q minus the y-coordinate from point P over the x-coordinate from point Q minus the x-coordinate from point P. That's our y2 minus y1 over x2 minus x1. And the y-coordinate from point Q is going to be 25 times, now it's not just times x if you think of this as x, so there's a couple different ways to do it. Let's think of this. The easiest way I think would be if we think of this as 3.5 and if we think of this as 3.1 and this is 3.05 and this is 3.01. Okay, that'll be the best way to make our lives easier. So now we have 25 times x minus 16. Whoops, sorry, I didn't need those parentheses there. After all, I was mixing up the two different methods of how to do it. 25x minus 16x squared. That's the y-coordinate for point Q, minus negative 69. That's the y-coordinate for point P, over the x-coordinate for point Q, we're just calling that x, and then minus, and then the x-coordinate for point P is 3. So you see, this is very similar to how we did problem number 1, as long as we adjust all of these x values and we add 3 to them, and we use 3.5, 3.1, 3.05, and 3.01. And of course, you can write this part as plus 69 instead of minus negative 69. So that's going to go into our calculators. We'll clear what's there. We have 25x minus 16x squared plus 69, close those parentheses, divided by, open parentheses, x minus 3. And then we can go back into the table. We can press delete to clear the numbers that were there. We only have 4 of them this time. We have 3.5. And the slope, or the rate of change, is negative 79. That's the velocity for that particular secant line. And then we have 3.1. The velocity is negative 72.6. And we have 3.05. Oops, that was supposed to be 3.05. And the velocity is negative 71.8. And we have 3.01. And the velocity is negative 71.16. Okay, now if you're not sure where these velocities are going, you can take another number that's even closer to 3. So you can go 3.00001 if you want to. You can get even closer than the problem asked you to get, and you'll get a better feel for what these velocities are heading toward. If I put my cursor over that number, I can see it's not really exactly negative 71. It was negative 71.00016. Okay, so back to the problem. I have a feeling we're going to be asked what the instantaneous velocity is. Oh, there it is. It was hiding. Find the instantaneous velocity when t equals 3. What do we think? This is our approximation. We think it's negative 71, right? Based on all those previous answers. And what are the units here? I suspect it's feet per second. Okay, so there we see two problems that have to do with finding the slope of a secant line and using that to approximate the slope of a tangent line. Now the third one is from your MyOpen Math. You're going to have different numbers, but the idea is the same. This is MyOpen Math number 4, the one we skipped earlier. And let's read the problem. We're going to be entering our numbers correct to 4 decimal places. Suppose an arrow is shot upward on the moon with a velocity of 46 meters per second, then its height in meters after t seconds is given by the equation h of t equals 46t minus 0.83 t squared. Find the average velocity over the given time intervals. Once again, that means average rate of change, and that means slope of secant line. Notice that they say they're giving us time intervals. So when you see the square brackets here, this is not an ordered pair. This is not a point with x and y coordinates 7 and 8. This is an x coordinate, the starting x coordinate of the interval, and this is an x coordinate, the ending x coordinate of the interval. Notice they're all starting with a 7. So that's telling us that our point P is a point 7 something. You want to find the y coordinate of the point? Going to have to plug 7 into this equation. And when I put 7 into that equation, I get 281.33. Now I didn't round, that's just the exact value. Okay, the second value in each interval is telling you the x coordinate of your point Q. So, for example, the first point Q is 8, something. Whatever we get when we take 46 times 8 minus 0.83 times 8 squared. But once again, let's go ahead and make ourselves a slope formula. The y-coordinate of point Q minus the y-coordinate of point P over the x-coordinate of point Q minus the x-coordinate of point P. And the y-coordinate of point Q is just going to be 46x minus 0.83x squared, and the y-coordinate of point P is 281.33. And then for the denominator, the x-coordinate of point Q is just going to be x, and the y-coordinate, or excuse me, the x-coordinate of point P is just going to be 7. So that gives us our formula, and we're going to put that in the calculator. Okay, so here we go. I typed it all in. Now I'm going back to my table. We can delete the ones that were there. And for this problem, we're using 8 for our first x-coordinate of Q, and the number we get for y is our slope. And then we're using 7.5, and then 7.1, and then 7.01, and then 7.001. So these points are getting closer and closer together, and looks like the slopes are getting really close to this number 34.379. And what we would have to do, because the calculator says enter the number correct to 4 decimal places, is you would need to go ahead and hover your cursor over each of these slopes and then look at the number on the bottom, because it'll show you more decimal places if it has them. Okay, so that's how we would complete that problem. So, I believe that's all we have to talk about. Your homework is MyOpen Math number 4, and I think it has 6 problems in it. They're very much like the ones we did in our notes today. Let me know if you have any questions. Thanks, everybody.